Well, if I knew that Augustine was so good with his geology, I would invite him over to geology to give a few lectures for us. So anyway, so be prepared for that. So, so now I'm going way back, and I'm going to tell a tale that was unraveled by one of my students, Tony Kubensky, with the help of myself and an Illinois State Geological Survey person, Joe DeVera. And so a long, long time ago, about 350 million years ago, southern Illinois was covered by a shallow seaway, which had a very high diversity of marine organisms that included the sea lilies. And there are sea lilies today. They're a group of echinoderms, so they're related to starfish and brittle stars, organisms like that. And they produce a lot of carbonate, which makes up the limestones that we find today exposed here, like the limestones that Andy was talking about over there in the LaRue Pine Hills. And so they're a big contributor to these carbonates, but they have a very interesting evolutionary history here in southern Illinois. Now, the group that I'm going to be talking about, and I'm talking fast because I kind of overestimated the number of slides that I needed for a 15-minute talk, is the genus Pterotocrinus. And Pterotocrinus is distributed throughout Illinois, southwestern Indiana, down into Kentucky. Here are some localities that were originally published on, discussing their occurrence in Mississippian age rocks, by the way, in this particular region. And here we see a cross-section which describes the Mississippian, or some of the Mississippian that's exposed in southern Illinois. And in particular, I'm going to be discussing the Menard limestone, which is here. It's the older of the rocks that I'm going to be discussing. And as you go up in section, you get younger and younger. And I'm also going to be discussing the Kincaid limestone. Pterotocrinus. Here is a very well-preserved fossil specimen of Pterotocrinus. And I say it's well-preserved because most of the time you don't find the calyx, or the head, of this particular organism or of this particular taxa preserved. Here we have the stem, which, if we go further down, that's where it would be attached to the... Oh, okay, all right. Here is the stem, and if we went further down, it would be attached to the seafloor. It extends up. Here's the head of the organism. It has branching arms that would extend even further up for feeding. And Pterotocrinus is noted for these very obvious plates that are part of the other plates that make up the calyx. And these plates are referred to as wing plates. And this is Pterotocrinus robustus. And it's called robustus because these wing plates are very robust. Here's another angle viewing the bottom part of one of the calyces of a Pterotocrinus. And here are the wing plates extending out from that. In this diagram, it shows it again. Here are the other plates which make up the calyx. But for the most part, the Pterotocrinus species, which have been identified in the Chesterian age rocks of the Mississippian in southern Illinois, are based on the wing plates only, because the calyces are rarely ever found preserved. So basically, we're digging around and we're looking for these little things that are the wing plates that have been left over after the Pterotocrinus has died. The calyx has disarticulated, broken up all those plates, scattered about. But these very distinguishing features, the wing plates, get left behind. Of course, they have morphologies then that we can use to help distinguish between one taxa of Pterotocrinus and another. Now, historically then, Pterotocrinus in this part of the Mississippian and these Mississippian age rocks have been used for biostratigraphy. And what biostratigraphy is by finding those particular wing plates, we can identify which part of the Mississippian we're in, or what the age of those rocks are. So we can identify whether we're in the Menard, or whether we're in the Kincaid, or maybe even in the Clore, which occurred in between those two ages of rocks, just based on the wing plates. And that, supposedly, is the evolutionary lineage going from the older rocks into the younger rocks. So, Pterotocrinus, a crinoid extant during the Chesterian series. That's the particular time interval which includes the Menard and the Kincaid, which I'm going to talk more about. The genus is most well known for its wing plates. That's because those are the things that were typically preserved and that we find in the fossil record. Evolution of these wing plates is believed to have evolved rapidly through the Chesterian, and it's because of that that geologists working in that particular time period are able to use them for biostratigraphy, or to determine where they are within the Chesterian, giving them biostratigraphic importance. But others, like my student Tony and Joe and I, also had questions about, well, what was driving that evolutionary change? Did these have a particular functional morphology that caused them to adapt and evolve, going from the Menard up through to the Kincaid? So, getting back again, I just wanted to put this back up to repeat. We'll be focusing on the Menard and the Kincaid. The reason we're avoiding the Clore and the Dagonia and the Palestine, the types of rocks in which we find these, the Palestine is a sandstone, so we don't typically find these wing plates in sandstones. Part of the Clore is a sandstone. However, there have been some wing plates found in the upper part of the Clore here, where it's more shaly, more carbonaceous. However, we weren't able to find enough to actually give them any sort of statistical significance in our analyses. And so we're avoiding the Clore for now and discussing the Menard and the Kincaid. These are some of the localities in which collections of those wing plates were made that included the Menard as well as the Kincaid. So after collecting hundreds and hundreds of these wing plates, they were measured meticulously, described. Measurements were taken of their total length, the thickness of those wing plates, and the length of the basal part of the wing plate. And then ratios of the total length to thickness and basal length to the thickness were calculated to do a little bit of comparison to see if we could differentiate populations of these wing plates that might separate them out for at least some biostratigraphic significance. And so just to give you an idea of what some of these things look like, and any of you who have gone out and done any fossil collecting, think about the rocks that you were looking in when you were looking for fossils, you know, kind of shaly type rocks, you know, that could break apart easily. And then look at these wing plates and think of whether or not you could differentiate that from a fragment of shale. When I first went out with Tony, I was like, so what are we looking for? And he goes, oh, we're looking for these things. And he showed me a couple, and I'm thinking, oh yeah, those will be easy to find. And so I spent half the day picking up little chips of shale and going, Tony, is this one of those? No, no, no. But once you get your eye cued in on what you're looking for, it gets easier. Okay, so this is Pterotocrinus menardensis. And this is a particular taxa, if you will, that was used historically to identify Menard-aged rocks. Why? Because through time it was only found in rocks that our early geologists thought was Menard in age. And there are other fossils in there that they use to kind of corroborate this. But this is menardensis. Round, thin, relatively thin, and you'll see relative to some of the other ones that we look at. So narrow, round, and a fairly short, this is the basal area that was measured for the length of the base. So you can see that relative to the length, it was rather short. Pterotocrinus chlorensis. So this was one that was thought to be restricted to the chlor formation, which we found very few of in the chlor and not enough to actually include it in our analyses. But we did find some of these. But we found them in the Menard, in rocks that we knew were Menardine in age. So that'll be part of one of the conclusions that's drawn here. But again, long, fairly short basal area, flat, broad, and narrow. P. Menard, undescribed morphology 1. And these are other taxa that haven't been described in the literature yet, or we couldn't find that have been described in the literature up to this point, but of different morphologies. But again, long, flat, and very narrow. Another undescribed morphology from the Menard, and this is very paddle-like. But again, thin and a narrow basal area. Furthermore, the same characteristics holding true for the Menard. And then last but not least, another Menard morphology, again being very narrow, although we start to see an increase in the basal length. So how are the Kincaid wing plates different, or those Pterotocrinus wing plates from the Kincaid different? Here's one taxa that has been reported historically from the Kincaid, Pterotocrinus edestus. And one of the things about the change in the morphology is an increase in the thickness, and they start to become pointed. Pterotocrinus tridecibrachiatus, same thing, pointed and much wider. Also, the basal area for attachment has increased significantly. Pterotocrinus wanasi, we're kind of missing the nice pointy area of this, fairly broad basal area, and again, thicker. And an unidentified, so far unidentified species from, again, the Kincaid, longer basal area. This missing the point here again, not really missing the point, but missing the point on the wing plate. And so compiling all the data and those ratios that we calculated, what Tony was able to do was identify populations that were distinct to the Kincaid and the Menard. There's a little bit of overlap there, but those grouped out quite well to distinguish those two different populations. So, based on this, it does have some sort of biostratigraphic application because the morphologies are consistent from the between the older rocks and the younger rocks. So, biostratigraphically, the morphology in general have some biostratigraphic relevance. P. menardensis is still considered to be isolated to the Menard, so using it as a good biostratigraphic indicator. There are certain species that are unique to the Kincaid as well, making them good biostratigraphic markers. But one thing we did find was Pterotocrinus chlorensis was occurring in the Menard as well as in the younger rock for which it was named the chlor, so taking away its biostratigraphic utility. So in the last few minutes I have here, functional morphology. It's been suggested that the function of these wing plates, one is the possibility of use as a rudder to keep this thing oriented up in the water column, help it kind of move around. It's a filter feeder. It spreads its arms out to capture particles of organics as they're floating through the water column. And also has been proposed that possibility that they may have used these things as a defense mechanism. Not that they would like shoot them out at their predators, but if you have something that's long and spiny and something's going to bite onto you, it would probably maybe dissuade them from doing that. So looking at the Menard morphologies, they're again narrow. They have a very short basal length. That's the area of attachment. And they're pretty flat. large surface areas, compared to the concave forms, which are typically pointed, much thicker, and having a fairly broad and long basal area of attachment that we see here, and they're thicker and more robust, suggesting that perhaps these were better suited to fend off predators. So what was going on around them that would cause them to do this? Well, in the late part of the Mississippian, we had the appearance of shell-crushing sharks, the diversification of that particular group of sharks, and perhaps this was the motivation for these crinoids to evolve this particular type of defense mechanism to ward off these shell crushers that if you're swimming along and you see these things floating around up there, might be nice to just kind of go along and mow them off as you're swimming by. So, Pterotocrinus wing plates of certain species in the Menard and Kincaid can be of some biostratigraphic utility, and as far as their application in the lower part of the Chesterian in the Menard, probably pretty functional as a rudder and evolved to be an anti-predatory device or mechanism as these predatory shell-crushing organisms became more abundant. So that's what was happening in your backyard about 50 million years ago. Or no, sorry, 350 million years ago. So thank you.